Hi, everyone. I'm Daniel, and welcome to the Light Your Candle podcast. I'd like to continue our discussion from the last episode on atoms. In the last episode, I introduced the notion that matter is made of atoms. Now I want to illustrate the illuminating power of the atomic idea. I want to start by looking at something we're all familiar with: water. Let's take a drop of water, about a half a centimeter across. If we look at the drop closely, we don't see atoms. We just see a smooth, continuous drop. If we take the world's most powerful microscope and magnify the drop roughly 2,000 times, the drop itself is now 10 meters across, about as big as a medium-sized movie theater. We still only see smooth, continuous water. Let's magnify it another 2,000 times. The drop of water is now nearly 25 kilometers across. If we look very closely, we see a kind of fidgeting or shimmering action. The water doesn't seem continuous anymore. In fact, it probably looks more like dancing couscous or a crowd of people at a music festival seen from very far away. To see the individual festival goers, however, we have to zoom in another 250 times. Now we can see the individual particles that make up what we know as water. And what do they look like? For this discussion, I want you to imagine them looking like little Mickey Mouse symbols. You know, the face with the two ears? This is because at the deepest level, water is made up of two different types of atoms stuck together: oxygen and hydrogen. We call this bonding of atoms a molecule, where the two hydrogen atoms are the ears, in this case, and the one oxygen atom is the face. We'll get to how they're different another time. But for now, just think of these two different atoms as the same way you would think of poodles and golden retrievers being two different variations of dog. We have enough here to keep ourselves entertained, I think. See, all the little Mickey Mouses in the water are constantly vibrating and jiggling next to each other. This is because, as we discussed last episode, the water has some amount of temperature to it. So let's say this is room temperature water, which means it has a room temperature amount of vibrations. So all the Mickeys are here, they're stuck together, and they're jiggling around and tagging along and bumping into each other. Let's heat the water up now. That is to say, let's make the Mickey Mouses dance faster. More heat, more vibrations, more dancing. The atoms start jiggling more now. More heat, even more jiggling. Now they're jiggling a ridiculously large amount, until the jiggling has become so great that they're no longer able to clump together anymore. They're no longer able to tag and hold on to each other. They're bumping into each other now that they're actually pushing each other away. The distance between them is growing and growing, until finally there is so much vibration, there's so much heat, that the Mickey Mouses actually just fly away from each other. They're actually pushing each other away from each other. We have a word for this process. It's what we call evaporation. Now the water has become steam. See, the water molecules are still there, but they're vibrating so much they bat each other away. They can no longer get close enough to each other to form a liquid. Next time you put the kettle on, imagine a whole bunch of angry Mickey Mouses streaming out of it. Or should I say steaming out of it? You see, the idea of atoms has now given us an understanding of how matter in the world can go from being in one state to a completely different one. It's just the vibrations of these atoms. Let's go the other direction now. Let's cool things down. So we take some heat out of the system. The Mickeys begin to vibrate less and less. As this is happening, they're also getting closer and closer together. This is because atoms over small distances attract each other. So as they get closer and closer, they also attract each other more and more. It becomes harder and harder for them to jiggle. At some point, there will be so little jiggling that all the molecules will just suddenly lock into place, like magnets locking together. We call this form of water ice, and the process is what we know as freezing. And because of actually the specific shape of the water molecule itself, the ice forms a crystal array where each molecule fits into a particular place relative to the one next to it. There's also a peculiar quirk with water in that when it freezes, it's actually less dense than when it's water, which is why ice floats. And if you think about that for a second, it's actually somewhat counterintuitive. You would think that when all the atoms are locked next to each other, that there wouldn't be very much, there would definitely be less space than when they're kind of free to flow and move around from each other. But that's actually not the case. You see, even though the water molecules are all stuck together, they still have good manners and are leaving space between each other. Whereas when it was a liquid, all that space would be filled up by loose Mickeys. Now, to be clear, even though the atoms here are stuck in a rigid structure, what we call a crystal lattice, they aren't standing still. They still have some temperature to them, which is to say they're still vibrating, only now they're vibrating in place, like dancing on the spot as opposed to really branching out and exploring the space. In fact, a better analogy might be a conga line of atoms, where each individual in the line is still dancing, having a boogie, but they're holding on to the person in front of them, and so on. Because of the definite order to the crystal, a definite structure. As we now increase the temperature again, the conga dancers vibrate more and more, start to dance more and more vibrantly, until they shake themselves out of place. And we call this process melting. See, depending on the kinds of atoms, the amount of heat required to turn a solid into a liquid or a liquid into a gas changes. That's why at, say, room temperature, iron is so solid. But you could have a bath in mercury. Don't do this. To finish, it turns out there is only one substance we know of that no matter how much we do, we can't take enough energy out of it to slow the vibrations down so that it solidifies. Helium. You see, no matter how much energy we take out of it, helium never stops vibrating enough to form that conga line. Must be a lot of fun at parties. I hope you all see now how amazing this idea is. With just a few sentences, that matter is made of atoms, and these atoms are constantly vibrating, we can understand what the universe is made out of on a fundamental level. And not only what it's made out of, but also how the stuff of the universe can transform from one state of matter to another and back again. How the water in the ocean gets up into the clouds, how it turns back into rain, falls back to earth, how it freezes and becomes the ice caps and glaciers, and perhaps closer to home, why butter is so solid in the fridge, but melts when you cook with it. Or how the wax of a lit candle heats and melts. I'll leave you to think about this. I'd ask that as you go about your day, you remember these things. Hold them in your mind as you look out at the world. You might find it contains a little more magic than you remember. Until next time, take care of each other.